Okay, here's the second example showing how we use Newton's laws again. Just a nice. This one's nice and simple in one dimension. The question reads as follows: two masses are suspended by the two massless cords as shown. Okay, so we have this arrangement where we have these two cords. This first one is carrying the whole load, and the second one is connecting the two masses. The top cord has a tension of 98 newtons, this one here, and the lower a tension of 58.8 newtons, right here. Calculate the two masses. Okay, so let's see how we do that. Well, let's first of all complete our diagram. How do these tensions act? Well, the tension in this rope kind of acts in these two directions. We'll call that tension one. And that tension is, in terms of how it's acting on this mass, is pulling upwards, okay? It's holding that mass up. And we have a second tension here, tension two. And again, it acts in different directions on the different masses. So it's pulling this mass M1 downwards, and it's pulling this mass M2 upwards. We have two additional forces then acting on these masses. So I'll mark that in these red arrows. And those forces, of course, are the force due to gravity. And the force due to gravity is just the mass times the acceleration due to gravity. So it's M1g here, and that's M2g here. So we now have drawn all the forces acting here, and the whole system is at rest. Okay, that's kind of implicit in what's in the question here. So we're going to use Newton's laws in order to solve this problem, and in particular we'll use Newton's second law. Okay, so Newton's second law will have that the total force, that's the net force here, that's F net, is equal to the mass times the acceleration. And we're now going to apply that to each of the two masses. So for mass M2, first of all, I need to write down also, we have T1 is equal to 98 newtons and T2 is equal to 58.8 newtons. Okay, so that's also given to us in the question. All right, so for the second mass, first of all, well, what are the forces acting in this problem? Well, in the upward direction, we have T2, and in the downward direction, we have M2G. So we have T2 minus M2G. What's that equal to? Well, it's equal to the mass times the acceleration, but of course the acceleration is zero. This thing isn't moving, so it's equal to zero. And we can just simply rearrange this to give us that M2 is equal to T2 divided by G, and T2 is 58.8. If you divide that by G, which is 9.8, you'll find that this gives us a mass of 6 kilograms. Okay, so that's our first mass. Now if we do the same thing for mass M1, so again, what are the forces? Well, we have T1 acting in the upward direction, and in the downward direction, we have this force due to gravity, M1G, and this force, which is the tension in the second rope, which is T2. So our total force, our net force, let's write the whole thing out again just for completeness. So F net is equal to the mass times acceleration. So this net force then is T1 acting in the upward direction, and in the downward direction we have T2, and we have M1G. And once again, this whole thing's at rest, so that this right-hand side of the equation is zero. And we can rearrange this now to give us an expression for M1. So M1 will just be equal to T1 minus T2 all divided by G. We know what T1, T2, and G are. They are 98, 58.8, and 9.8 respectively. And you'll see that I've chosen the numbers here nicely. So this is equal to 6G, this is equal to 10G. So we get 4G divided by G, which just gives us then 4 kilograms for the first mass. So that's the problem. Again, it's nice and simple. We're just working in one dimension, but it's just important to recognize how these tensions act differently on the two masses. That's the key to solving this problem.